Welcome everyone. In this video lecture, we will continue our last video which is based on the NMOS pass transistor logic for the logic 1 transfer in the earlier video. So today we will discuss the pass transistor logic for the logic 0 transfer. Okay. So I want to just continue with the some brief idea what we have covered in the last video lecture. So in this case, we have used a logic 1 transfer circuit, okay, basically a basic NMOS pass transistor in which we are giving input to this point. So this point is, we have already observed, this point is our drain, gate and source, and the maximum voltage when we are giving the VDD value across this side, drain side as a input, and we are giving a high value clock, high value of clock, okay, that is our, simply we can say, the VDD. Then the maximum voltage across the source in will go up to VDD minus VTN for logic transfer, logic 1 transfer, okay. So we have assumed that initially at Vx at t equals to 0 is 0, and Vx at t equals to infinity, it will come VDD minus VTN. So for that one, we have already derived the formula, okay, like this. So I will share the link, the description menu for the derivation, all these things. So we will get this one, and from this one t is the value as a function of Vx, and we can also find the value of Vx, okay, from the same expression. So it will come like this, okay. So it will come like this. So below, this one is our time formula, and then Vx formula we will derive from this same expression. So it will come, and the graph between Vx and t will be like this, okay. So now today we will try to think about the condition when we are giving the V in 0, okay. So now in this situation we have assumed that initially the circuit is able to transfer logic 1. So now in this case what we are assuming, that I am writing here, let Vx at time t equals to 0, it is the capacitor Cx is charged up to maximum, that is our VDD minus VTN, and we are giving V input 0, okay. The V in, that is our, this one is our 0 voltage, and the clock is also giving the high value of clock, okay. So once again I am repeating, we are assuming that at this node, at soft node, we can say the voltage is Vx is equal to logic 1 level initially. So Vx at t equals to 0, it has the maximum value, that is our Vmax, we can say Vmax, VDD minus VTN. Now a logic 0 level is applied to the input. A logic 0 level is applied to the input. We are giving a logic 0 level at the input side. And now the clock signal, that clock signal we are giving to the gate in to the pass transistor goes from 0 to VDD, from 0 to VDD at t equals to 0, and the pass transistor starts conducting when this VDD value will be high, that is our VDD. So what we observe, that initially this value is 0 and this value is charged up to this Vx, okay. So in the logic 1 transfer, this side is drain and this is the current is flowing, okay. We are saying this one is id like this, but in this situation the capacitor is fully charged and this is logic 0 transfer. So it start discharging this capacitor, okay, and the current will flow from this side, okay. And this, during that time, we can observe that this end become our what, drain in, because current is flowing from this side, drain, this in obviously gate terminal, and this term is our source terminal. So initially the transistor is in saturation. Now in this case, in this case it is in the saturation region, okay. For logic 1 transfer you can go, Now in this situation, the transistor, the pass transistor, that is our, we can say MP. So this MP, the transistor in this situation is our linear region. Okay, how? For linear region, what is the expression? We know the VDS, VGS minus VT. Okay, clear. Once again, I am just drawing the MOSFET ID VDS curve. Every time I am drawing this is VGS minus VT. This side is our saturation. Okay, and this side is our, you can say, linear. Okay, so when VDS is less than equals to VGS minus VT, it is in the saturation, sorry, linear region, linear. And this one for saturation, VDS should be greater than equals to VGS minus VT. So here what we observed that this VD is VG minus VT. Okay, S is common. So VD minus VS, VG minus VS. So VS cancel. So now drain voltage is basically this one is Vx and Vg is our VDD minus VT. Okay, so one can say this value is also means initially it is VDD minus VT. VDD minus VT. Initially this value is VDD minus VT, but current is flowing and this capacitor start discharging. So it goes when it is just less than this value, it will become linear region. So that's why this transistor in this case for logic zero transfer, this transistor will be in the linear region. So ID will be in the linear region. Okay, because this capacitor start discharging through this side. So now what we can do? Now we can write the current expression ID in the linear region, that is our mu n cox, okay, w by l. Okay, simple linear expression I am first writing vgs minus vtn into vds minus vds square by 2. This one is the formula. Okay, you can also modify this as a the whole term mu n cox w by l kn. Okay, now vgs we can write it, get voltage is VDD. So we can write it VDD minus VTN. Okay. Into VDS. VDS means what? VX. Okay. VD is VX and S is 0. So simply VX minus VDS VX square by 2. Okay. One more line we have to write to make it simpler. Okay. 2 is there. So the expression will be Kn by 2 twice times of VDD minus Vx square. Okay, so this one is the expression ID, the current that is flowing in the circuit. Okay, in addition to that, one more current, because this one is capacitor and current is flowing from this side. So we can directly write the ID value is what? Simply minus Cx dVx by dt. Okay, because the current is flowing from 0 minus Vx. So, okay, Cx d 0 minus Vx. Okay, or you can like write like d by dt of initial voltage 0 minus, so this one is id. Okay, capacitor current. Okay, I will just making diagram here for Cx, current is flowing like this, id, this potential is 0 volt and this potential is what? Vx. Simply starting we are using a Vx. So okay, so now these two one these two these two will be same. Okay, so now what we will do? what we will do, these two will be same, so what we can write, minus cx dvx by dt equals to kn by 2 twice times of vdd minus vtn vx minus vx square. Okay, now we have to find the value of time. We have to find the value of time, and Vx all very similar to the logic one transfer. Okay, so from this expression, what we can write? We can write dt. Okay, okay. So dt I am writing in this side. So what we can write? Minus twice cx. Okay, minus twice cx by kn. Kn, and here I am writing dvx. Okay, and the whole term, that is our twice vdd vtn vx square. Okay, this one is one important observation we can say. Okay, dt equals to, okay, so now we have to integrate this one for the calculation of vx. Okay, so how to solve this one? First, you have to start with the dt. So dt, so initially we assume that at time t equals to 0, so it will from 0 to t it will vary. Okay, and the other term, what we can write for the in right hand side, kn. Here vx is initially we have assumed that it is value is vdd minus vtn, then after it will go up to vx, some voltage vx. Okay, then dvx I am writing here. Okay, and then after this we have to write. So what I am doing here, minus term is there, here also minus term, so I am taking minus vx common. So what we can write, vx minus twice vdd minus vtn. Okay, clear? So this should be plus, or one more thing, and this if you integrate this one, it will be simply t. Okay, t, or you can write t t0. Okay, I am not escaping any point, any step. Kn integration again, vdd minus vtn to vx dvx. Okay, okay, one more line, vx into vx minus twice minus vtf. Okay, so this one is some integral. Okay, you have to integrate this expression. Okay, this integration we have to solve. Clear? So how to solve? So this one dvx by vx by this. Okay, so to solve this problem, okay, I am starting. So if we integrate this one, what we can write here, I am writing t. If you integrate this one t, one more line I want to write for more clear picture. This one we have to solve by using partial fraction concept. Okay, so what we can write, this can be written as dvx a times of vx. Okay, plus, okay, plus b times of dvx by vx minus twice vdd minus vt. Okay, I will solve this one step by step. Basically this one is the thing. Okay, a dvx. Okay, just we have written in terms of partial fraction type. Okay, so I am saying this one is equation number A. Okay, so how to solve this one? What we can do for this type of thing? What we can write? A times of bx plus b times of, or we can write a times of, okay, bracket, plus b times of bx divided by what? Vx into Vx minus 2, Vx minus 2 plus Vtn, which is equals to 1 upon, we have written this one as a this, okay, so which is basically our Vx into simple, okay, means what I am writing, this one by this one, this is basically 1 by this, so this can be written as a by this plus this. Okay, so now what we can do, this term and this term will be cancel out. Okay, so one more line we can write a times of Vx minus twice times of b times of Vx equals to 1. Okay, now we have to find the value of a and b. So for a and b, what we will do, ab we can write avx minus twice a vdd minus vtn plus bvx. Okay, then a plus b vx minus twice a vdd minus vt equals to 1. Okay, now see, the Vx coefficient is 0 in the right hand side. So what we can write, a plus b becomes 0. So what we can write, a equals to minus b. Now this one is our constant term which is equals to 1. So we can write minus 2a, simple partial fraction concept. Those who don't know the partial fraction concept, they can go to the partial fraction concept. So minus 1 by twice vdd minus vt n. Okay, so b value will be automatically, so a is this, so b equals to 1 by, so I'm writing, so what we observed, a equals to minus 1 by twice times of vd minus vtn. Okay, so b equals to just minus this, so 1 by, okay, so now we have calculated the value of a and b. Okay, so now we can solve the integral very easily. Okay, this was from equation 1. I'm writing here, from equation A, the t value can be written as twice cx by kn. Okay, and we can write like this, a value is there, so this one is constant, so 2 vdd minus vt n. Okay, a is there, and what we can write, dvx by vx, where this value will be very from vdd minus vtn to vx. Okay, plus, okay, some plus b times of, so I am writing here only, b is our 1 by twice vdd minus vtn. Okay, twice VDD B value, then integration dVx by, here also the limit we have to write VDD minus Vtn to Vx. Okay, now I will take some space to solve this problem. Okay, here I'm writing. So from equation 1, we can write as t. I'm writing here. From t equals to twice Cx by Kn. Okay, and now what I am taking this as a what, comma. So what we can write? 1 by twice VDD minus Vtn. Okay, this one is okay. Now this one integral, minus sign is there, so keep it there. Okay, we will go, it's dvx by vx. Okay, plus again vdd minus v, sorry, vtn, vdd minus vtn. And this one is a very simple integral vx. Those who are beginner, they can go each, with each and every step, and those who know everything, they can do it directly. So this t value can be written as these two to cancel, so cx by kn vdd minus vtn. Okay, then this value will be minus log x. Okay, so what I am writing now, I am doing one final step. Okay, so like this one, we can write as minus ln vx. Okay, minus ln vx and plus ln, this should be vx minus twice vdd minus vtn. Okay, and for both having the same limit, so I am just putting limit here. Okay, we can write like this also, integral property. Okay, so this one is the t expression. Okay, time expression we have already written. Okay, so in the next page we will write the time expression that what we observed. The t value will be, cx2 will be cancelled out, so kn vdd minus vtn. Okay, and then what we can write? Okay, one more line I am writing, that we have observed that 2 vdd minus vtn. Okay, minus log vx, and we have to integrate with vdd lower limit to vx. Okay, so this one can be written as log vx minus twice times of vdd minus vtn, and ln a minus b, so we can divide with vx. Okay, okay, simply this we can write. Now we have to put the limit value. Okay, so now here we have to be very careful because we are going for the final step. So VDD minus VTN as it is. Okay, now here we have to write Vx. Okay, for the upper limit, what we can write? Ln Vx, so Vx, so no need to disturb, twice VDD Vx, first limit is over, minus, now in the second, ln A minus, yeah, Now Vx will be this VDD minus VTN, okay, minus 2 VDD minus VTN. Now we are writing Vx equals to VDD minus VTN by VTN. Okay, so then after we have to write Cx by Kn VDD minus VTN as it is. Okay, this value will be same and this value will be A minus B and A minus B. So if we solve, okay, one more VDD minus ln, okay, because VDD minus Vn, VDD minus VTN minus twice. So minus VDD minus Vn minus VDD. So this VDD minus VTN in the both numerator and denominator will cancel out. So it should be minus 1. So now again if we change this one and if we solve this one, simply a simple mathematics, Kn times of VDD minus VTN, and this if minus 1 will come here, so it should be twice times of this ln twice times of VDD minus VTN, okay, and minus this should be minus Vx by Vx. Okay, so the value of t, what we observed, this one, this one is the value of t. Okay, so okay, the value of t, I'm using different color, black color. T value is Cx times of Kn VDD minus VTN ln twice times of VDD minus VTN minus Vx by Vx. Okay, this one is the expression, and if you plot this one, the for zero transfer, okay, if you go like this, okay, and this point is our, this one is a Vx and time axis, and this Vmax will be in the starting what we have in VDD minus VT, so it will decrease up to 0. Okay, so this one is the variation of Vx as a function of time. We can write a variation of Vx as a function of time during logic zero function, during logic zero function. Okay, so now in some, suppose we have to find the fall time, okay, for this one, okay, suppose fall time. So if we say t 90%, one concept is there, t 10%, okay, so fall time t, or we say tau fall equals to t 10% minus t 90%. Okay, so this can also be found, okay, in which at t 90% your, what we can say, the value of node voltage, that is our Vx at t 90% will be 0.9 times of Vmax. At t 10% the Vx value will be 0.1 times of Vx. So you can also find the fall time also, okay, by using this same formula. Okay, now so for example, the fall time for the soft node, okay, the fall time we have to find Actually, this one is the circuit. Okay, now this video is taking time, so we have to find the fall time. Okay, for 0 and VDD. Okay, tau fall. So tau fall at so T 90%, what should be value? T 10%. We have to write. So for example, if this one is the thing, so any time period time at 90% we can find as Cx, okay, VDD minus VTN ln twice VDD minus VTN, and this one minus Vx is become minus 0.9 times of Vmax. Vmax is what? Vmax is VDD minus VTN. So 0.9 times of VDD minus VTN, okay, divided by Vx, 0.9 times of VDD minus VTN. Okay, so if we solve this one is Cx, okay, Cx upon Km ln, this should be cancel out, 2 minus 0.1, okay, 2 minus 0.1 means ln 1.1 by 0.9, okay, so this one is the value for this one. Similarly, if we find for T 10%, okay, Cx Kn VDD minus VTN, very similar expression we have to write, twice times of VDD minus VTN and minus 0.1 Vx, okay, means VDD minus VTN. Only you have to put the value of Vx, like 0.9 Vx, and Vmax is our VDD minus VTN by 0.1 times of VDD minus VTN. Okay, so again this should be cancelled, 2 minus 0.1, 0. 2 minus 0.1 means 1.9 by, so it should be Cx by, okay, means how to find the fall time. Okay, so it should be 2 minus 1.9 by 0.1 or simply ln 19. Okay, so tau fall we can find out T 10% minus T 90%. So this one is common, so Cx Kn, actually this one is given in that Kang book, so I am also trying to make this one. So is this one, the first value will be simply say ln 19, we can say ln 2 minus 0.9, oh sorry, 10%, so it should be 19, okay, ln 19. And if we solve this one is ln 1.22, and if we solve this value it will come nearly 2.74 Cxy. If every value is given, you can find the fall time also. So this is the expression, this is the expression for the fall time, okay. So we can, but here we have to say for T 90% Vx will be 0.9 times of Vmax. At T 10% it should be this. Okay. And where Vmax is VDD minus VTN. So we are putting VDD minus VTN. This one, all this Vx value. Okay. Similarly here 0.9, 0. Then it should be 1.1 by 9, 1.22. Means here we have written 1.22. So this should be our Cx by Kn VDD minus VTN into ln 1.22. Add everything will be same, and this will be 19, ln 19. This one will be ln 19. Okay, so we have did like this. Okay, so this is all about for the zero transfer. You have to go for these steps. Okay, so this is all about this lecture. So you can go step by step and also try to follow the book of Gang book. So this is all about this video lecture. So thank you for watching this video. Thank you.